Now, in this video, we're going to talk about graph. Right now, you're seeing a graph on a decimals. The graph is 1000 equals to x plus 1, x minus 5, and x plus 5. And then the denominator factor gives us the asymptote, the vertical asymptote of the graph. Let me label all of these. So we have the first one gives us x equals to -1. The second one gives us x equals to 5. The third one gives us x minus 5. Now, let's look at this asymptote and see how does the multiplicity of the factor will change the asymptote, the behavior next to the graph behavior next to the asymptote. Now, I'm going to cover the other two asymptotes. Let's just look at one. X equals to -5. So right now the factor is x plus 5 to the third power. So that means this is going to be multiplicity of 3. If multiplicity of 3, when the graph nearby the asymptote, the direction 1 is going up, the other one is going down. So that means they're in a different opposite direction. But if I change the multiplicity of 2, which is an even number, look, they both going up to the same direction, right? Now let me change this to 1, which is an odd multiplicity. Let me change that to 1. Look, the direction will change back to 1 going up, 1 going down. So if I change that to 5, still, if it's odd number, they're going to go to the different direction when they come nearby the asymptote. But if this is an even number, they're the same direction. They both going up. Or let me change to 8. Still, they both going up. So here is the pattern of the asymptotes. Specifically, it's the behavior next to the asymptote. So if the factor in the denominator polynomial has odd multiplicity, the function, the graph of the function, to be more exactly, goes in opposite direction. Which is similar to 1 over x, because when we have a 1 over x, the vertical asymptote, look, here is the vertical asymptote in y-axis. 1 is going up, and then on the other side is going down. So, on the other hand, if the factor in the denominator have even multiplicity, the function goes in the same direction, which means they're adjacent to each other. This is similar to 1 over x squared. Now, let's take a look. 1 over x squared, which is the reciprocal square function, the asymptote is still y-axis, this one, right? They both, when they're getting close to the asymptote, they both going up to the same direction. And these two graphs is adjacent to each other. And this two is opposite direction. One going up, the other going down. Okay, so this is the thing that we need to know. This is the local behavior when it comes to nearby the asymptote. So things should include on your rational function graph. One is the intercepts. So intercept, we have an x-intercept and y-intercept. When it comes to x-intercept, we also have the local behavior. Local behavior, which means determined by the multiplicity. If it's even, that was similar to the quadratic function. If it's odd, will be similar to the cubic function, which is either cross or a bounce. Okay, second thing is the asymptote, the vertical asymptote. The vertical asymptote also gives us the local behavior, which means if the multiplicity is even, that means it's going to be similar to 1 over x squared. They're going to be the same direction, either both going up or both going down. If they're odd, the local behavior will be similar to 1 over x, which is goes to the different or opposite direction. Okay. Third thing that we need to include is the horizontal asymptote or slant asymptote, which is determined by the leading term of the rational function. 4, we also need to consider the removable discontinuity. Okay, so after we include these 4 things, we should be able to draw a graph. Okay, now I want you to sketch the graph of fx equals to x plus 2 times x minus 3 over x plus 1 squared x minus 2. First, we want to have x-intercept. Let's do y-intercept because y-intercept is easier. We let x equals to 0, so we have 2 times negative 3 over 1 squared negative 2. Simplify it, we have 0 and 3. Second, x-intercept. X-intercept is we want the whole function equals to 0. Since this is a rational function, that means we just need to let the top equals to 0. Then we have 2 x-intercept. One is negative 2, 0. The other one will be 3, 0. And we need to be careful when it comes to x-intercept. We also need to consider the multiplicity because that determines the local behavior. So since they both m1, that means this is going to be a cross. Okay, next thing is the vertical asymptote. Vertical asymptote is let the denominator equals to 0. So we have 2 asymptote. Asymptote is going to be a 9, so we can write it as x equals to negative 1 and x equals to 2. And when x equals to negative 1, we have m2. So that means m2 is going to be similar to, this one, sorry. The reciprocal square function, that means they're going to the same direction. And the x equals to 1, equals to is m1, that means this is going to be the opposite direction. Now, the next one is the horizontal asymptote or slant asymptote. We need to check that by the leading term. So the leading term, it will be x squared over x to the cube, which is similar to 1 over x. So that means the end behavior is going to be similar to 1 over x. That means the horizontal asymptote would be y equals to 0. And let's check if there's any removable discontinuity. So there's 2 points that is undefined. One is x cannot equals to negative 1. The other one is x cannot equals to 2. And they don't have the same factor as the numerator. So that means there's no removable discontinuity. So now let's draw the graph. So for the graph, we know that the ending behavior, it will be similar to 1 over x. Well, let's draw the asymptote first. Horizontal asymptote is y equals to 0. So in order to separate them, so you will see it's not overlap, but actually y equals to 0 should be overlapping to the x-axis. So I want you to see that, so that's why I don't have it on here. So now vertical asymptote, we have x equals to -1. Oops, this is so bad. Okay. And then we have another one, x equals to -2. Okay, since it's asymptote, I want you to use a dashed line to represent it and mark this is the same direction or adjacent to each other. This is the opposite direction. Label that. So this is 2. And then we have y-intercept. Now, when we start in the graph, I'm going to use a blue pen. Y is 0 to 3. That's our y-intercept. X-intercept at -2 and +3. -2 is in here, and the behavior is cross. At -3, we have another x-intercept. It's going to be a cross. Now, when we look in this graph, it's a little bit hard to start with. We don't know where should we start the graph. Should be, here's a couple options. Is that going to start in here or start in here? Because we know that this is going to be look like a little rand. If we don't know, one way to do it is substitute a number to check out, is this going to be above 0 or below 0? Okay, another way to do it is check out all of the evidence on the graph. So I know that this part doesn't have x-intercept. So that means the graph is not going to pass this line. So that means there's no way this is going to be a cross or a bounce because the intercept doesn't exist. We can just make one up here. And that means also in the middle part, we have a y-intercept on the top. So that means most likely this graph will be on the top. So if it's on the top, so that means the graph has to be in this side, the middle. Okay, and now when we look at the asymptote, this asymptote has the same direction. So that means this graph should start with also on the top because they should have the same direction. They're both going up. So then, and then have a cross asymptote, cross the x-axis. Now, look at the right side of the graph. They have the opposite direction. So since this one is going up, so that means on the other side of the asymptote, they should start with going down and then cross this point, get to here, because the end behavior is similar to 1 over x. Remember, we proved that in here. So that means that goes to infinity and approaching to 0. So that would be the graph. Another way to do it is always check your answer. Now, let's take a look. So the graph that we have is y equals to x plus 2, x minus 3, oh, not 4, and then x plus 1 squared, and then x minus 2. Now, take a look. See, this is exactly what we just drew, right? Look. The middle part is look like similar to parabola going to the top. The curve is on the top on the left, and there's another curve on the lower right. So that's the graph. And then I would like to have a second example. Oops. So here is the second question. Kx equals to 5 plus 2x squared over 2 minus x squared. So the first step is you will try to factor the polynomial function. So the upper one, there's no common factor, and we can factor them. But the one that in the denominator, we can factor it as 2 plus x times 1 minus x. Now, after you factor, it would be easier for you for the next steps, such as, let's find the x-intercept. X-intercept is when y equals to 0. So that means we want the function equals to 0. If the function equals to 0, meaning that the numerator equals to 0. So when we solve it, we have x equals to, nope, let me solve it. Minus 5 on both sides. Oops. So we have a 2x squared equals to negative 5, and then x squared equals to negative 5 over 2. So we know that square, they can have a negative number, so that means there is no x-intercepts. Okay, now y-intercept. Y-intercept is when the x equals to 0. So we have 5 over 2, which is 2.5 for our y-intercept. Next is a vertical asymptote. Vertical asymptote is when the denominator equals to 0. So I have x either equals to negative 2 or x equals to 1. And the multiplicity are m1, so that means the vertical asymptote is going to be in the same direction or adjacent to each other. And then horizontal asymptote was determined by the leading coefficient. The numerator leading coefficient, not leading coefficient, leading term would be 2x squared. The bottom one would be negative x squared, because they got a negative in here, so when they multiply together, the highest power gives you a negative x squared. So, simplify it, we have negative 2. So that means the horizontal asymptote is equals to y equals to negative 2. So the next thing is we need to check the removable discontinuity. So we have this guy, x cannot equal to 2, and then x cannot equal to 1. And now let's look at them. Do they have the same factor as the numerator and the denominator? If they have the same factor, then that will be your discontinuity, removable discontinuity. So we don't have that. So that means we don't have any removable discontinuity. So that's why you want to factor the polynomial first as your first step, so that you can find the vertical asymptote, also the removable discontinuity. All right, next, let's draw it. So we have a graph. We got the coordinate plane, y and the x. Horizontal asymptote, we have negative 2. Oops. So let me use a dash line to do that. And then we have a horizontal asymptote at x equals to 1. This is 1, 2. So let me draw this asymptote. And then we have a horizontal the other two is a vertical asymptote. And then we have a horizontal asymptote. I'll just go ahead and use this one, since there's a 9 in here. So this is a negative 2. I know it's not proportional, but that's okay. And then we need to label that. We know that in these two vertical asymptotes, they need to have the same direction. Now, next thing is we want to label the x-axis, the x-intercept and the y-intercept. So there is a one y-intercept here, which is 0, 5 over 2. Okay, so where should we start it? So when we start it, there's no x-intercept. So when we started, we try to start with the one that gives us most of the information. Oh, sorry, I made a mistake in here because this part is not the same direction. If it's M1, should be similar to this guy, 1 over x. So that means they should have an opposite direction. That's why when I look at the graph, I was like, no, something's off. So this should be an opposite. This also should be an opposite. Okay, now let's look back to the graph. When we start this, the vertical asymptote cut the graph into 3 parts. 1, 2, 3, the left, middle, and the right. And then we look at which one gives us most of the information. In this case would be the second one. And we know that they don't have an x-intercept. So that means the graph stay on the top above the x-axis. So that means this is your first graph. And then the second one can be the first part or the third part, which is the left part or the right part. It will be the same. So we know that this asymptote, the behavior nearby this asymptote, the direction should be the opposite. So on the right, it goes up. So that means on the left, it goes down. And the graph is approaching to -2. So let's draw a better sign. It should look like this one. The graph is approaching to y equals to -2. Similar to the right part, which is the third part of the graph. It should be going down because you want them to be the opposite direction, because one is going up. So that means on the other side of the vertical asymptote should going down. And then the end behavior is approaching to y equals to -2. So that would be the graph. And always check your graph with a decimals. See if it's correct. Okay, that's it for this section. I'll see you in the next video.